Okay, let's get started. This is Monday, March 28th, ECE 231, and this is lecture number 14. And today I'm going to talk to you about the analog to digital converter peripheral called the ADC, which is one of many different peripherals that are located within the Atmega 328P chip. And of course, this is a key subsystem for the digital thermometer that you're building for lab number 3. So just to let you know, or to remind you, Wednesday's class, L14, I won't come in planning to lecture on any new material. We'll just use that day either as a day off from lectures, or as a help session, or as a Q&A. So just feel free to come in on that day and ask me any questions you have at all about the lab, and I'll answer them, and perhaps I'll use some of the time to show you some of the testing that I've done when I built lab number 3. Okay. So the key sensor that you're using for this lab is the TMP36, and this is the product web page from SparkFun. That's the vendor where we get them. We didn't get them. I don't think we got them from SparkFun this year, but they're one of many distributors of this device. One thing about this is if you happen to be familiar with small transistors like the NPN 2N3906, 2N2222, 2N3904. If you've had your hands on any of those, you'll notice that they look just like this little temperature sensor. It's just a small 3-terminal device. And so it's very easy. We didn't ship any small transistors in your kits this year, but in another course that I teach, I use small transistors in this sensor, and many students make the mistake of picking up the transistor and not looking right on there to see TMP 36. You want to see that on there to identify positively that you've got the right device, and not some transistor or other device that happens to have the same form factor. Okay, so one thing about this, note that these things cost $1.50. This is an inexpensive little temperature sensor, so we're not trying to get high accuracy with this lab. So if you find that when you build this thing, you can't get it to within several degrees of a thermometer, even 5 degrees of a thermometer, don't worry about that. Also, if you find that the temperature is fluctuating over several degrees just sitting there in the room, don't worry about that. We're not trying to get high precision here, and it's because you have so many other subsystems here that you have to make work that I don't want you to spend a lot of time worrying about the accuracy. So in terms of systems and subsystems and components, let me just say a little bit about systems and systems engineering. In this project, you are building a complete system, right? And it does the job of measuring temperature and then providing that display out on primarily on the 4-digit 7-segment display, but also on the serial monitor. So if you think about that whole thing as a system, you obviously have a number of critical subsystems. And so you'll have the temperature sensor and the associated analog to digital converter, which is part of the chip, and then the software that runs that. You can think about that as a subsystem. So this little temperature sensor is one component in a subsystem as part of a larger system. Other subsystems, well, of course, the Arduino Uno with all the hardware and interfaces it has, that's a subsystem. And then the 4-digit 7-segment display is a subsystem. And the switch that you use to sort of choose between displaying Celsius and Fahrenheit, you can think about that as a subsystem as well. Or you could think about that as a component in another subsystem. But the point I wanted to make here is that when you think about this, there are really 3 levels the way to think about this. If you think about one sort of big block or big box, that's the whole thing, the whole system. Then you have these subsystems, For example, the 4-digit 7-segment display, the temperature reading subsystem, and then you have the individual components, and everything has to work. All those pieces have to work, and they all have to work together. So when you're building something like this, there's a fair amount of complexity. You'll be using probably be using ports B, C, and D. You've got digital input and output. You've got analog input. You've got a switch. You've got a pull-up resistor. You've got some kind of fancy coding that we talked about last week for making the 4-digit 7-segment display do its thing. So what you want to do is try to think about this thing, even on a piece of paper. Draw one block that represents the whole system, and then try to draw separately. Try to draw blocks as subsystems, and try to test the individual subsystems by themselves. That is, take the 4-digit 7-segment display, wire it all up, and run code that just checks that. Convince yourself that that part is working. Then add the temperature sensor and the analog-to-digital converter, and then test that. And test that by writing the result out in different ways to the serial monitor. Make sure that part works. Then start bolting them all together. And the reason why I say that is, if you just start out with a bare breadboard and a blank slate, and you try to write the code for everything fresh, there's just too much complexity. So you want to build this up subsystem by subsystem. Okay. So more about this sensor. Just a little bit about this description here. So this device, it provides an output voltage that's linearly proportional to the Celsius temperature. Okay, and well, there's a simple linear relationship between Celsius and Fahrenheit, so we'll be able to also connect it to Fahrenheit. Okay, I did have a question that someone just, I guess we had a raised hand. Someone have a question?
Hi, Professor. Yeah, I do have a question. So, what you essentially said is that we need to develop code in a test-driven kind of way, so that whatever function we are writing, we are testing it. Or you essentially wanted to say like whatever the function we wrote on the C program, then we need to check that if it's outputting on the device or on the system or not. Like, I didn't get a clarity on that.
I think you may be asking how you should architect the software, whether you should put everything in main or put things in functions. When I do this, I tend to do a little of both. I'm not requiring you to use functions. So if you wish, you can put everything in main, or you can put things in functions. I'm going to be showing you example code today where I'm making a lot of use of functions, because you test out a function. Once you got it working, you sort of carry it around with you and use it in other programs. So I would encourage you to use functions as modules, and that can become part of your testing also. But the main point I'm trying to make there is that when you build this whole thing with all the wires and all the code, you turn it on and it doesn't work. And you say, well, what the heck is wrong? So you really need to test things piece by piece. So if, let's suppose you turn it all on and it doesn't work. First there's problems getting it to compile, but let's suppose it compiles, and then you're just getting some kind of wonky, result, flashing display. It doesn't sort of make any sense. So you want to check things piece by piece. And so start with your temperature sensor. Check the output voltage from the temperature sensor with a voltmeter, and just see whether you have a voltage that's increasing with temperature. That'll tell you whether that part is working. Then take the temperature sensor and write its digital value or its analog value or its corresponding temperature. Write that out to via the UART to the serial monitor. That way you're checking that part of the system independent of the flashing 4-digit LED display. And then you say, okay, I know this part is working. Now I'm going to go and I'm going to check the 4-digit 7-segment display. So it's a divide and conquer approach. You want to test the subsystems piece by piece. And sometimes this means writing a separate piece of code, a separate program, just to test one of the subsystems. That's okay. I mean, when I built this one, I probably wrote four different programs to test the various pieces, and then I kind of bolted them all together. And it's because the whole system by itself just has too much complexity. And it's just too easy to have a stray wire or a problem, or just some little problem with your code, and you're trying to figure that out. What you do is you want to convince yourself, yes, this part is working, therefore the problem is somewhere else. Okay, so back to the description of this temperature sensor. I just want to note that it tells you that it provides a typical accuracy of plus or minus 1 degree C. So that means about plus or minus 2 degrees Fahrenheit. Okay, and that's at room temperature. But then over a wider temperature range, it's got an accuracy of plus or minus 2 degrees C, which is about plus or minus 4 degrees Fahrenheit. So over a wide temperature range, the accuracy of this device is only about plus or minus 4 degrees Fahrenheit. So when you do have it set up and you look at it and if you put a digital thermometer there, you could easily be off by plus or minus 4 degrees. Don't worry about that. We are building a measurement device, and in the specification I gave you, I told you to show a display that has 3 significant digits, 98.6 and then C or F. So I want you to show 3 digits, a tens place, a ones place, and then a 0.1 degree place. So that your display is going to have a resolution of a tenth of a degree. So you'll be able to show that it's 60.1, 60.2, 60.3, and so forth. So your display has a resolution of a tenth of a degree. But the accuracy of this thing is only going to be plus or minus 4 degrees. Okay, so it's got a resolution of a tenth of a degree, a precision of a tenth of a degree, but an accuracy of only 4 degrees. So what is that like? Think about your watch, right? You wear a watch, and of course nowadays most of if you're wearing a smartwatch, then it's getting its time from the internet, so it's accurate in time. But if you think about a mechanical watch that you wear, or even perhaps a digital watch that doesn't automatically set the time, you could easily be off in time, incorrect in time by several minutes. But that watch can still be telling you time to within a tenth of a second, right? So it still has a resolution. It could be a tenth of a second, even though it could be off by several minutes. And this is the case with a lot of measuring devices. So there are 2 separate issues here. There's the resolution, that's the degree of quantization that you can tell, whether one value is higher or lower than the other. And that's much finer than the actual accuracy. Okay, so, but sort of a takeaway from all this is that even though I'm asking you to build a display that's going to show temperature down to the tenth of a degree, this inexpensive sensor is really only accurate to within plus or minus 4 degrees. So you will be able to see small changes, but you still may be off by several degrees. Okay, a little bit more on this sensor. So this is also from the data sheet, and I encourage you, I want you to go and look up the data sheet. You can go to the SparkFun website. You can just Google the TMP36 sensor on SparkFun, and then they've got documentation on this, and go take a look at the data sheet. So here's what it tells you. It tells you it's going to give you an output of 750 millivolts at 25 degrees C. Okay, so I've just noted that over here. So the output voltage is 750 millivolts at 25 degrees C. And it also tells you that it has an output scale factor of 10 millivolts per degree C. So I've just noted that here. So we can put both of those pieces of information together. The output it's 750 millivolts at 20 degrees C, 25 degrees C. And then for every degree C above 25, the output voltage will increase by 10 millivolts. So that you put both of those pieces together, and this becomes an equation that allows you to express the output voltage as a function of the temperature in degrees C. So get yourself a multimeter. I mean, you don't have to turn anything in involving those analog measurements, but get a multimeter and hook it up and check that output voltage. And that's another way of getting temperature out of this. Of course, what we're after is an automatic, embedded computing-based way of doing it. This little device has 3 wires, so it's got a ground. VS is the power supply, okay? And we're going to be using, for VS, we're using 5 volts, which is the power supply on the Arduino Uno. And then V out is your temperature, your voltage signal. That's an analog voltage that we're going to be sampling with the analog to digital converter. Okay. If I take this equation here and I just plot it and make a little table here, this shows us the output voltage as a function of temperature in both Celsius and Fahrenheit. And if you take this expression here, it's trivial to take that and then rewrite that output voltage as a function of degrees Fahrenheit, because the conversion between Fahrenheit and Celsius is a simple linear relationship. So this table shows us, even though this thing operates, it's designed to operate up to 125 degrees C. That's hot. That's hotter than boiling, significantly hotter than boiling water. We're only interested in operating it over a limited range, right? Really down to about here. And the reason why I'm just asking you to build this thing to operate over a range of positive temperatures that are below 99.9 degrees. And that's simply based on the number of digits you have in your 4-digit 7-segment display. You want to use one of those digits to indicate a C or F, right, for Celsius or Fahrenheit. Then you have 3 digits for temperature, and we want to have tenths of a degree. So you're just showing tens place, ones place, and tenths place. And that's the reason that I asked you in the specification to only have this operate over a fairly limited range. Now, right now, today, it's in New England, it's unseasonably cold. It could actually get below 32, so you could have a negative number in degrees C. If you took it outside, it would just read 0. You wouldn't be displaying a negative temperature. Okay. So we're gonna just say a little bit more about this sensor, and then I'm going to start talking about how we sample it with an analog to digital converter. Just regarding the pinout on this. I'm telling you, don't rely on this figure. Always go to the data sheet and make sure you understand which pin is which when you put this device into your circuit. Okay. All right. So now let's just talk briefly about analog versus digital converters. So this device is an analog. It's an analog sensor, meaning the output voltage can vary continuously as a function of time and amplitude. Now, I'm showing an example of an analog signal that happens to have positive and negative values. Let's see, is it possible for this sensor to have a negative value? I suppose if T were low enough, this might go negative. It won't be for our purposes, but I just wanted to show you contrast the distinction between an analog signal on the left. And it's just one that, its amplitude can vary continuously over any range, right? And it's also defined at all points in time, okay? So we say that an analog signal is continuous in time and in amplitude. And when we say continuous in time, we mean if we look at any segment, say this point and this point, right? Then the domain of that signal as a function of time, it contains an infinite number of time instants between 2 points in time, because it's a continuous signal. Okay, I'm talking continuous in a mathematical sense. It's also continuous in amplitude, meaning between any 2 amplitude values, you can draw a continuous line in between. That contrasts with digital signals that we represent on a computer for a couple reasons. When we take a signal like this and we sample it to put it into a computer, what we do is we take snapshots at different instants in time. We sample it, we sample it, we sample it, right? And so basically, you just take a snapshot at all these instants in time, okay? And so you convert the signal from a signal that is continuous in time to one that is discrete in time, meaning you're only looking at it at these discrete instants in time. So by sampling it with a computer, take a sample, 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 you're converting it from continuous time to a bunch of snapshots in time. So that's one thing that's different about it. The next thing is, you know, if you look at a digital signal like on the right, we know that it's going to be a pattern of ones and zeros. How many ones and zeros would you use to represent, let's say, this value? Well, that depends on how many bits you're using in your analog to digital converter. The analog to digital converter inside your Atmega chip is a 10-bit converter. So 10 bits has 2 to the 10th or 1024 different values. So what happens is we're going to be taking this signal, we're going to sample it at all these points, and then we're going to, each one we're going to represent as one of 1024 different possible values. We'll be representing those amplitudes as 10-bit words. So basically, the process is that we're taking this signal continuous in time and in amplitude. First, we make it discrete in time by taking samples. And then we also make it discrete in amplitude or quantized in amplitude because we don't allow for all possible amplitude values. We really take each instantaneous amplitude and we ascribe to it one of 1024 possible values. So there's a certain approximation that takes place when we go from analog to digital. This will make more sense as we get into this. And so let's now start to talk about analog to digital converters. So the basic idea is you're going to have an input voltage like we just looked at. It's continuous in time and in amplitude. And you send that into this ADC, analog to digital converter, and you're going to get an output, which is going to be a binary number that has n bits. Okay, so when you see a line with a sort of diagonal through it with an n, that represents n bits. And so you have an 10-bit ADC in your chip, but I'm going to start out with the example of a 2-bit converter. And what happens is this input signal is compared to a reference voltage. And then based on its value relative to that reference voltage, it's ascribed one of 2 to the n possible different values. So if we take the example of a 2-bit analog to digital converter, right? If only 2 bits, it means it's going to take the input signal and it's going to divide it up into 4 possible values. So there's going to be vref, vref over 2, vref over 4, and 3 vref over 4. It takes that whole range of possible inputs between 0 and vref. Vref is what's called a reference voltage. It chops that up into 4 equal size units. Why 4? Because we have 2 bits, and 2 bits gives us 4 possibilities. And so if the input voltage is between 0 and vref over 4, the output is going to be given the value 0, 0 in binary or 0 in decimal. If the input is between vref over 4 and vref over 2, it's going to take that signal and it's going to encode it as value 0, 1. 0, 1 in binary or 1 in decimal. And so on. If it's at this level, it's going to encode that as 1, 0 or 2. And finally, if it's at the highest level, it's going to encode that as a 1, 1 or value 3. Okay. So inside the computer, it's storing it as 2 bits of information, and they can be represented either as binary or as decimal. Okay. So now an important figure of merit here is the step size. It's the spacing between here and here. Okay. What is the step size? In this example, it's vref, that's the total span, divided by 4. Right. So this step size, v step, is a quarter of vref. Right. So we're going to find this is an important figure of merit because this tells us about the precision of the analog to digital converter. Okay. What we were doing here is we were forming output voltages here. And the way we were doing that is we were taking Vin and we were dividing by V step. Now, Vn is a value between, well, between 0 and vref. It's an analog value. It's a floating point value. as you'll see in the next example, VREF is an analog floating point value. So we're taking a ratio between two floating point values, but the result is an integer. And that's kind of a key subtlety here. The reason why the result is an integer is because it's represented by a finite number of bits. So what's happening here is we actually form D out, which is this digital word, okay, by taking we're taking one floating point divided by another floating point, and we throw away the remainder. And another way of just writing that is the D out is V in divided by VREF over 4. So this stuff is going to make more sense to you when we look at some examples on the next slide. But before I leave this, I just want to give you these three sort of different equations. We have the step size, okay, right? And that's going to be VREF divided by 2 to the n. And then we have D out. This is the way we actually do the conversion. And then once we've got D out, if we want to convert back to the input voltage, which is what you often will have to do when you want to make sense of a reading, we come back and we recompute V in by taking our output, our D out, and we multiply that by D step. I'm going to show you some examples. Okay, so let's start out with a 2-bit analog to digital converter, and suppose that VREF is 5 volts. So we have an input signal. It's going to be between 0 and 5 volts. Well, let's start with that. Let's assume it's between 0 and 5 volts, and VREF is 5, and assume that n is equal to 2. Okay, so if n is equal to 2, I have 2 to the n, or 4 different values. So the step size, the quantization here, is going to be VREF divided by 4. 5 volts divided by 4, 1.25 volts, or we'll often think in millivolts, it's 1,250 millivolts. Okay, so this is just taking the previous example and putting some numbers on it. And so this table down here would just show you, shows you the conversion. I've just taken what I'm shown in the chart and I've sort of, represented it with a table. So suppose I have input values between 0 and 1.25, right? Then they're going to be here. Those are going to get mapped to an output of 0, 0 in binary or 0 in decimal. And if the input is between 1.25 and 2.5, that's this range here, then the output is going to be mapped. It's going to be assigned a digital representation 0, 1, okay, or 1 in decimal, and so forth. Now, what would happen if the input signal were negative? In that case, it would be assigned a value of 0. Right? It would be quantized as 0, 0. And if the input value were greater than 5, right, then it would sort of, hit the rail, and it would be assigned a value of 1, 1. Now, will the analog to digital converter, what's called the front end, will this circuitry be harmed by an input value below 0 or above VREF? It depends. It depends on the specification of the ADD converter. But typically, you want to design it so that the input voltage is in the range, in the measurable range between 0 and VREF. Okay, let me just show you two examples where we take an input voltage, we convert it to a digital value, and then we kind of convert it back. So let's suppose that we have an input voltage of 2.6 volts. So I'll just sort of show that right here. So 2.6 volts, it's going to get converted up here to 1, 0. Okay, 2.6 volts. Oh, wait a minute. What happened here? Oh, I've got a typo on here. This should be 1, 0, not 1, 1. But let's sort of do this, kind of analytically. So I'm looking at this red box in the lower right. How does the conversion happen? We're taking 2.6 and we're dividing it by our quantization or our step size of 1.250. And if you take those two and you do that ratio and you throw away the remainder, the fractional part, you'll get 2, which in binary is 0B10. Okay, so the 2.6 voltage gets represented as 1, 0. Now, when you convert that back, right, when you say, okay, well, I want to know what does this represent as a real analog voltage? What was that corresponding input voltage? Well, you're going to take that 2, right? It's two bits. It's a count of 2. Multiply that by your step size, and you get 2.5 volts. And notice that 2.5 is different from your input, right? That's called quantization error. You started out with 2.6 volts. You digitized it, represented it on the computer. When you convert it back, you're down to 2.5. You've lost some of that precision. That's a result of your quantization error. And what happens is as a result of this quantization, when you interpret those bits to represent the analog voltage, you could be off by 1 step size. So this conversion process can have an error as high as 1 quantization level, right, which is 1.25 volts. So the smaller the quantization level, the smaller the error you could have. Okay. Now, what is that going to mean for our application? Well, let me back up a few slides here, and I want to show you our temperature sensor. And I want to talk about the sensitivity of this device. So over here on the left, we notice that the scale factor is 10 millivolts per degree C. Okay, so it's 10 millivolts per degrees C. So if we wanted a precision, or if we wanted a resolution of 1 degree C, then we have to be able to tell the difference between 10 millivolts and the next 10 millivolts. Okay, that sensitivity is also about 5 millivolts per degrees Fahrenheit. Put another way, it takes, for every 1 degree change in Fahrenheit temperature, we're going to see 5 millivolts of increase. If we want this device that we build to be able to discern a 1 degree change, we have to have an analog to digital converter that has a quantization error or a step size smaller than 5 millivolts. Okay, we'll come back to that. Okay, all I want to do is, there's a slide I just showed you. I just want to compare what would happen if we had the same analog to digital converter, but we had a reference voltage of 1.1 volt instead. So we have our input voltage, Vn, and our reference is 1.1. Well, in this case, we're still going to quantize it into 4 different levels, but the step size, which is Vref divided by 4, it's only 1.1 volt divided by 4. So it's only 275 millivolts. So the difference between this one and the previous one is that this case, where we had Vref is 5, it's taking 5 volts and it's dividing it up into 4 levels. Each of those levels is 1,250 millivolts wide. It's pretty coarse and it's got a fairly high quantization error. If we decrease the reference voltage down to 1.1 volt, then the error in this is a smaller value. It's only 275 millivolts. Now, both of these are kind of impractical because they only have 2 bits associated with them. Okay, let's start to look at our A to D converter. So it's a 10-bit A to D converter, and you have different choices for the reference voltage. And so most commonly we'll be using 5 volts, and you can use 5 volts for lab number 3. So it has 10 bits, so there are 2 to the 10 or 1,024 different values. So when you hook it up, you're looking at an input voltage swing that's between 0 and 5 volts, right? And it's going to take that and it's going to sample that, and it's going to ascribe it to one of 1,024 different values. So there's a lot of different values here. What's the step size, the quantization here? It's Vref divided by 1,024. So that's 5 divided by 1,024, which is about 5. It's 4.88, about 5 millivolts. Okay, so this particular device, it will have a resolution of about 5 millivolts. That means that it takes about 5 millivolts of change in that voltage from the input in order for this thing to go from one digital value to another digital value. Put another way, the least significant bit of quantization is corresponds to about 5 millivolts. Okay, just a little bit more about this. What it's going to do is, if let's suppose that we have a very small voltage between 0 and, I say 5 millivolts, but it's 4.88 millivolts. It would turn that into all zeros, right? In binary, which is all zeros in hex, okay, or 0 in decimal. On the other hand, if the input were to jump up by about 5 millivolts, so it's 5 millivolts above 0, that would get coded as all zeros in a 1, or 1 in decimal, and so forth. So for every 5 millivolt increase in that voltage, it gets encoded by 1 bit level higher, so that the encoding goes from 0 all the way up to 1023. Okay. The very last slide like this I'm going to show you, right? And I realize we're kind of way down in the weeds here. The very last one would be if I take this same analog to digital converter, but instead of having a reference of 5 volts, I drop it down to 1.1 volt. Okay. So now I have a 10-bit analog to digital converter, so it's got 1024 different levels, but VREF is down to 1.1 volt. Okay, so in this case, the step size is VREF divided by 1024, or down to a millivolt. So this would be a much more sensitive device. It's able to discern changes from 1 millivolt to the next. Go back a slide. This one can only discern changes from about 5 millivolts. So if you have a change in the input signal less than 5 millivolts, you won't see it. It won't show up as a change from 1 bit position to the next. It takes about 5 millivolts to see the least significant bit change. Whereas in this one, it's more sensitive, 5 times more sensitive, approximately. So you can see a 1 millivolt change. So why is that important? Well, if you recall from slide number 3, when we talked about our temperature sensor, it has a sensitivity of 10 millivolts per degree C, which corresponds to 5 millivolts per degrees Fahrenheit. Okay, so let's sort of take that, knowing that's the sensitivity, and ask, if we used this sensor here, if I use this one, right? What's the smallest temperature change that I'd be able to measure, right? Well, this analog to digital converter, it has a quantization of 1 millivolt per bit, right? 1 millivolt. So it can discern, it can measure 1 millivolt changes on the input side. And so if we take that and we combine that with this information, we can figure out what does 1 bit change correspond to in temperature. So we have a quantization of 1 millivolt per bit, right? That's the smallest change that we can discern. And if we divide that by 10 millivolts per degree C, that's from the sensor, right? That's this value here. It tells us that this has a resolution of 1/10 of a degree C. And or that would correspond to 2/10 of a degree in Fahrenheit. So if we configured our 10-bit analog to digital converter with a reference voltage of 1.1 volts, we would actually be able to see changes down to about 1/10 of a degree C, or 2/10 of a degree Fahrenheit. And if you're thinking about the thermometer that you use to measure your body temperature, right, you certainly care about that 1/10 of a degree, right? Like if you're not feeling well and you put a thermometer under your tongue, or if you have one of the new ones that are contactless and you measure the temperature of your forehead or something, you really want to know your body temperature down to within 1/10 of a degree, because you feel differently, right, between 99.0 and 99.9, right? I certainly feel a lot more ill at 99.9 than 99.0. So if you were building a real temperature, like a body temperature, you would really care about these level changes. You'd want to really have a display, and you'd want to be able to trust the measurement of this thing down to 1/10 of a degree, okay? Now, on the previous slide, I'm going to jump back. That one had a resolution of 4.88, or about 5 millivolts. So if we only have 5 millivolts, what does that correspond to in terms of measurement resolution? 5 millivolts per bit divided by 10 millivolts per degree C. It's half a degree C or 1 degree Fahrenheit. Okay, so what that says is you really aren't able to measure for real temperature changes unless they're an entire degree. Okay, so does that mean that when you build your A to D converter, you should set it up with a voltage reference of 1.1 or 5? Well, if you were after measurements where you really wanted to be able to believe all of the digits in your display, right? I mean, your display is going to kind of look like this, right? And if you really wanted to believe that tenth of a degree, then you would want to go for this case with a smaller step size, and you want to use a reference voltage of 1.1. You can do that or not. It's okay if you go with a coarser step size. You use the 5-volt reference, and your last digit, right, is not real. It's okay if you do that. And the reason why I say that is I know that some of you have already set up your sensor on your desktop or your bench, and you're finding that output voltage is just fluctuating from measurement to measurement by several degrees C. So I don't want you to spend a lot of time trying to stabilize this and get this thing to be precise down to within a tenth of a degree C. I do want you to configure your display as if you were capable of doing that. But there are techniques that we could do. You could take a bunch of samples and average them together, but that's sort of more work for you. So it's up to you how you choose to do this. Okay, I did have a question. Someone had raised their hand on Zoom. Is there still a question there?
Yeah, Professor. Just when we are like lowering the VREF from like 5 to 1.1, we are getting more accurate measurement. So why can't we like reduce the VREF to like somewhere like something dV like 0.0001?
Yeah, so it's a question of what's available. Well, one question is, what is the range of input voltages that you have to deal with in the real world? Okay, and so if we were to go back to slide, I'm going to jump back to slide 3, this one here, and ask what is the range of voltages that we actually have to contend with. It's about, in millivolts, it's about 500 millivolts to 900 millivolts. So that is the output of this sensor. When you hook it up, it's going to range between 500 millivolts and about 900 millivolts. So a reference value of 1 volt or something like that nicely fits this. If you use a reference value of 5 volts, you kind of have a lot of ceiling where you're just sort of wasting space. If you dropped it down to something smaller, then you would be chopping off part of that range. So it's a matter of finding the range of voltages associated with your sensor and then matching those with what's available on the analog-to-digital converter. Okay, so what I want to do here is start to talk about analog-to-digital converters. Briefly, I'll talk about them in general. Then we'll dig in and look at how your analog-to-digital converter works on your chip, on your Arduino board. Okay, and so now here for this experiment, for lab number 3, you're still using the Arduino board, but keep in mind it's the chip, it's the Atmega 328P chip on the board that has all this in it. The rest of the Arduino board just has power supplies and crystals and and USB to serial interface that we care about. But it's the chip, and this is inside the chip. Okay. So when we talk about A to D converters, there are sort of 2 different kinds. There's what's called a flash analog to digital converter and a successive approximation. Now, what a flash analog to digital converter does is it takes an instantaneous snapshot of an input signal. It sort of does it all at once. And what it does is it creates a ladder network. And it takes VREF and it connects that through a series of resistors. Notice that you have all these resistors that are in series between VREF and this would be ground, right? Instead of having negative VREF, it's ground. And so what we've got here is a ladder network of 4 identical resistors. And so what happens here is you're going to have VREF up at the top. You'll have 3 VREF over 4 here, VREF over 2, and VREF over 4 down here. And so what happens sort of in brief is you take this input signal and you're comparing it at once to all those different values in some voltage comparators. And if VREF is above those reference values, it turns on the bit associated with those comparators. Okay, now I may have said that way too fast for it to make any sense to you. That's okay. The point here is that this flash A to D, what it does is it has a certain amount of complexity inside, and all at once it's able to give you a digital output that gives you a digital representation of that input in a flash. These only work for a small number of bits, though. That's the issue. And so this is an example where it's just a 2-bit flash A to D. And so they tend to be quick, but they don't have an awful lot of precision. The other type of analog to digital converter is the successive approximation analog to digital converter. It's actually quite a bit more elaborate. And what it does is you take your analog input voltage, and then you have your reference, and what you want to do is come up with a binary input that determines, you know, what fraction of that reference this analog input voltage is. And so the way it works is it starts out, it takes an initial guess at what that input value might be. So it's a guess represented as a digital number. And then it converts that to an analog signal, and it compares that to that analog input. If the guess is too low, then it bumps up the guess. If the guess is too high, it brings it back to lower, right? It's sort of like, you know, if I asked, if I'm thinking of a number between 0 and 100, I said to you, guess a number between 0 and 100, right? And you said, you know, your first guess might be 50, right? That might be a good guess for you, right? And then if I said lower, then you'd say 25, right? And I might say higher, and then you might say 37. And what you're doing is a sort of a binary search where you're kind of quickly closing in based on my instructions, higher versus lower. And that's what happens inside this closed loop. The details of that are not at all important to us. But I just wanted you to see that there's this word flash or direct conversion analog to digital converter and a successive approximation ADC. And a successive approximation is more accurate and you get more bits out of it. And that's what you have inside this device. So to sort of get into the chip and how it's described, okay, first of all, what the data sheet and sort of the sales specs will tell you that this is what it's got inside it. It has a 10-bit successive approximation ADC, which is that thing I just described. It's going to be a self-contained module. We don't need to worry about the details of it, but we have to program it to operate with parameters that we want for VREF. There's a timer that we have to give it and things like that. Now, how many analog to digital converter channels are there? Well, actually, this should say PDIP, not DPIP. PDIP. That stands for Plastic Dual Inline Package. And so this chip here with 28 pins on it, that's called a Plastic Dual Inline Package. Dual means it just has 2 rows of chips, each one in a line, 2 rows of pins, each in a line. That's the kind of chip that's on your Arduino Uno, and that's also, you have another one of these in your kit. You can also get what's called a quad flat pack version. Quad because it actually has chips on 4 sides, and it doesn't plug directly into a breadboard. You need a special kind of socket for it, and that one has 32 pins. They're both Atmega 328Ps, but one of them is 28 pins and the other is 32 pins. And the key difference is the one that we have, it has 6 analog to digital converter channels. And if you happen to have that quad flat package, it has 2 additional channels. So that's what this is about. Where are our channels? They're up here. So if you look in the top right, port C, like all the ports it does, it has multiple functions. So you can use port C as general purpose digital input and output, but port C also corresponds to these 6 analog input channels. So you could connect an analog voltage like the output of this temperature sensor directly to any one of these pins, and you could read that using this analog to digital converter. If we look at the diagram on the left, we're talking about this subsystem here, okay? And I just want to show you some things about how it's shown connected. You can see how it's got this bus here. It has a 6 with a diagonal line. That means it's got 6 wires, okay? And it shows those things coming right down as port C, pin 0 through 6. So port C, pin 0 through 6, those pins function as the GPIO for port C, but those pins also function as the analog to digital inputs. It also shows 2 additional inputs, right? ADC 6 and 7, and that's if you were using this other package that we're not using because it doesn't plug into a breadboard. Okay. There are 3 other wires here. There's AVCC, that's analog VCC. Okay, now up at the top of the chip, notice that you have VCC. VCC is the voltage that powers up the chip, and VCC is just in electronics. VCC is just what we use for the positive voltage to power something up. It has historical significance. It comes from the use of bipolar junction transistors. I guess you saw some of this already. You know that you have a bipolar junction transistor and you also have a field effect transistor. And bipolar transistors have collectors, emitters, and bases. And CC refers to the common collector. So it's language that's historic. It even precedes when I was born, but it stays around. It's what we talk about when we refer to the positive voltage supply, VCC. And that's 5 volts, right? On your Arduino Uno, it's connected to 5 volts. When we put a chip on a board, we're going to give it a 5-volt supply. The analog to digital converter has its own separate power supply, and it's supposed to be powered up approximately the same as VCC. On the Arduino Uno board, these are actually tied together. There's actually a connection, and you don't change that. It's internally powered up. But the point is that the analog to digital converter has its own power supply connection, and it has that because there are different techniques that can be done using what's called bypass capacitors and other devices to try to make these analog to digital converters somewhat immune to noise, because analog signals are kind of susceptible to picking up noise just in the environment. But I just want you to sort of know that on your Arduino board, you don't have to worry about that. It's internally connected. Okay, there's a ref. I'm going to say more about that in a minute, but we've been talking about what that means. Then there's also ground, which is going to go, to ground. This device is already going to be grounded on your Arduino Uno. Okay, digging into the data sheet. Tons of information on the data sheet, and it's fairly complicated to get through. I just wanted to show you some pieces of the data sheet, tell you a little bit about it. Okay, so first of all, 10-bit resolution, we know that. Okay, the conversion time, and I just bring this up, it takes between 13 microseconds and 260 microseconds, which is a quarter of a millisecond. So you can run this with different clocks, and that'll determine how long it's going to take to actually do a conversion. And why does it take time to do a conversion? Well, this is a successive approximation analog to digital converter. So we're going to actually have to give it a clock, and that'll determine how fast it updates. Okay, just some things about it. It does have its own temperature sensor input channel. I'll say more about that in a bit. Okay, what I want to do here is, you know what I'm doing? I'm going to actually have you. I'm going to ask you to read all of this on your own time, right? Offline, and I'm just going to kind of walk you through some of it. What I want to do is I want to make reference to this picture that we showed before, where you can think about one of these successive approximation converters. You only have to worry about an analog input voltage, a VREF, we know what that is, and there's the binary output that we care about, okay? So if we look at on this complicated circuit from the data sheet, What I've done is I've shown you where those three pieces are, right? I'm showing you where VREF is here. I'm showing you the analog input voltage here, and I'm showing you the binary output here, okay? And I'm sort of drawing a circle around that, or an oval, because the idea is what you see in that red oval also represents this, okay? And the reason why I'm doing that is it's important for you to be able to look at a data sheet and say, okay, I can kind of relate to this on some level, right? And when you first look at this thing, it has a great amount of complexity. So I just wanted you to be able to appreciate that this thing that we've been talking about at a high level here, right? It really has only VREF, it has the analog input voltage and the binary output that we care about, and you can see where they are in this diagram on the left, okay? Now, what else is going on here? Well, this analog input voltage is actually coming off of an input analog multiplexer, meaning you can take your inputs, they can be from these analog to digital input channels, and it shows 0 through 7. Your chip has 0 through 5. If you had the quad flat package, you'd have 2 more. There's also, it can take the input from ground or from an internal temperature sensor or something called a band gap reference. Okay, just questions here. I've got a question that has come up on chat. For project 3, are we not able to use port C for the 7-segment display since we need these pins for the temperature sensor and ADC? So you only need one of those 6 analog input pins because you have 1 temperature sensor, 1 analog input voltage. So you have available 6 of them. You have 6 pins available in port C. You can mix and match those between digital GPIO and analog to digital converter. So for project 3, you're going to use some of those as digital GPIO, but you need to reserve one of them for your temperature. So that's the idea. And the way this analog to digital converter works is you take all these various inputs. There's a device called an input multiplexer, and you tell it which of those many analog inputs you care about, and that one gets fed to this input device. So that's how it chooses from among a sort of a whole series of possible input voltage. You choose the one you want, and I'll show you how we configure that. Okay, VREF, there are a number of different choices for VREF. You can use AVCC, which is tied to VCC, which is 5 volts. So you can use a 5-volt input. There's also an internal 1.1 volt reference. Inside the chip, it actually has the ability to create a 1.5 volt. That's why in the previous slides, I showed you examples of 5 volt and 1.1 volt. And there are even other possibilities there as well. But most commonly, you'd use 5 volts or 1.1. Okay, what I'm going to do next is, hold on just a second here. Just changed the heater in my room, and it's I'm in a basement office, and I'm being frozen out today. I'm going to walk you through some slides that show how this analog to digital converter works. And I just wanted to thank Mr. Safir Naimi, who is from Iran, and he's the founder of a website called nicerland.com, which you can check out. And he's also the co-author of one of the co-authors of your textbook. And so you can go check out nicerland.com, and he has sections on our chip, the AVR family of chips. He also has some sections on other microcontrollers as well. But he has some slides that he created of some nice animations, and it's courtesy of that gentleman that I'm able to use these slides. So I'm gonna build this up for you piece by piece. So here is our analog to digital converter, and it's shown just as a rectangular box, but it's the same thing conceptually as this, right? You have an analog input. You know, that's the voltage we care about. We want to digitize that. We want to get it onto the computer as a pattern of 1s and 0s. All right. We also have our VREF, right? And then we have our digital, you know, our output bits. Okay. So that's what's shown here. We have VIN, we have VREF, We have our 10 output bits. And I've also added a clock on here because it's a successive approximation. It sort of does things. It takes a number of steps to actually do a conversion, so it needs a clock. Okay, so the input, the voltage input, there is a wide variety. We have 5 different ADC inputs, right? They correspond to pin C0 up through pin C5. If we were using that other version of our chip, you know, the quad flat package, we'd have 2 additional inputs. But these are the analog to digital inputs. There's an input multiplexer, and what we do is we're going to be configuring a register called ADMUX, analog to digital multiplexer. That's a control register. We're going to configure that, and we're going to tell it which of the inputs that we want. So, for example, if we wanted to connect our input to ADC0, right, we would program these. There are 4 bits. We would program them 0, 0, 0, 0. If we wanted analog to digital converter ADC5, right, we would program these 4 bits to be 5, which would be 0, 1, 0, 1. That's 5, and so forth. Okay. In addition to those external inputs through pins, there's also it's a very, I don't want to say crude, it's a very coarse temperature sensor on board the chip. So the chip actually has its own temperature sensor, but it's only good to like 10 degrees Celsius. So what it's able to do is give a very coarse indication of temperature. And that would be used if you had an application where you're generating heat and you were really concerned that the chip is on a board and the board might be getting so hot that it's potential to damage something. There is a temperature sensor built into the chip that can be used to measure that. It can't measure fine, changes, but it can measure sort of tens of degree change. And if the thing were getting to be so hot that something was going to get damaged, you could use that as a way of shutting down some functions. So that's what that's for. Okay, there's also an input of 1.1 volts that you can sample that to calibrate the A to D converter. And you can also have just ground as an input, again, for calibrating the analog to digital converter. So one of the things we have to do is configure this register down here to tell it which of these many inputs we want to sample. Okay. Also the reference, right? We have 3 different choices of reference. There's an internal 1.1 volt reference. We can sample the 5 volt power supply that we have, right? Or we could actually supply an external reference, something that we hook up from the outside if we want, and use that as the reference. And how do we choose from which of these we want? Well, there are 2 pins here, right? There are 4 possibilities and 2 pins. So in this ADMUX register, we're going to use pins 0 through 3 to tell us which input we want, which from a series of inputs. And then we're going to use pins 6 and 7 to tell us which reference that we want. Okay, one more. Okay, this is a 10-bit analog to digital converter, right? We're dealing all along here. We're dealing with an 8-bit microcontroller, meaning it thinks and its natural unit of storage is 1 byte. 10 bits is too much for 1 byte, so it stores the output in 2 bytes: analog to digital converter low and analog to digital converter high. The thing can only function in chunks of a byte. 1 byte, not enough for 10 bits, so it uses a full 2 bytes. It actually allocates 16 bits. So a lot of those bits are 6 of them are unused. But this is how you get an output. It's stored in 2 separate bytes. All right, this thing I've got in the red box, when you read it, you have to make sure you read the low byte before you read the high byte. Otherwise, you get incorrect results. And I'll show you how to take care of that. Okay, last thing on here is the clock. This A to D converter needs a clock, and we have our system clock, which is very high. It's 16 megahertz, right? 16 million cycles per second. That's the chip on board the Arduino Uno, and this thing, it can only be clocked as high as 200 kilohertz. So what you do is you just have to take this 16 megahertz and then divide it down with what's called a prescaler. And so we have to configure this. So to operate this thing, we have to configure this, and that just tells it what clock rate to use. and then we have to configure this one, and that's going to specify which input we want, and we're also going to specify these bits, which tell us what reference we want. Okay, you set those things up. I'll give you the code to do that, and it'll be very much, it's analogous to the way we configured the UART. Remember when we talked about the UART, there are all kinds of possibilities. It's how many ASCII bits you want, how many stop bits you want, whether you have parity bits and the baud rate. And we just sort of wrote those once. We tucked those numbers away in some subroutines or some functions, and I said, just copy these and use them. This is going to be the same thing. I just want you to know that there's all this configurability here. But what we're going to do is take all of this, set it up for some default values that we use, tuck those away in some functions, and you'll just be able to use them. Okay? So let's talk about this AD MUX register. Okay, I'm going to go back to the previous slide. It's this one down here. Let's just talk about what we have to do with that. So that's used for three things. We've got these bits here on the right, MUX 0, 1, 2, and 3. They're used for input select. All right. It's also something called right or left justify and vref selection. I'll show you those one at a time. So first we have input select. And so you just have to use these 4 bits to choose one of those many inputs. Okay, I'll give you an example. The next one, ADLIR, is right adjust or left adjust. And here's the idea. You've got a 10-bit output from this A to D converter, and it's fitting into 2 bytes. So it's fitting into 16 bytes worth of memory. And so the question is, do you want to have those right justified, meaning all of them are sort of over to the right, and you have zeros on the left? Right? That's right justified. That's how you'll normally do it. And that's the default. That bit is 0. You can also set that bit as 1, and it's left justified, right? So all those bits are sort of pushed over here, and you have the empty bits on the right. So for most of your applications, you would just use the default. You wouldn't even have to worry about this. But there is a situation where you may want to use ADLAR equal 1, and that is left justify, meaning you may want to take all the bits and push them way over here. And that would be a case where you want to operate this only as an 8-bit analog to digital converter. So it's 10 bits. This is the least significant bit here, ADC 0, right? That's the least significant bit. Okay, that's the one that changes the most. And then you have your most significant bit way down here, ADC 9. If you only wanted to operate this, let's see, that's MSB. If all you cared about was operating this as an 8-bit, that is, you're saying, throw away the last 4 bits. I don't care about them. I'm really only looking for bigger changes. Well, what you could do is left justify this and then just ignore those bits. Only read this upper byte. And if you did that, you would actually have an 8-bit A to D converter. So that's one application why you might care about this. It's not something that we're going to use in the class, but I just wanted you to see it. Okay. I've drawn all over the slide here, but the very last thing is we just have to select vref. And you can choose the internal 1.1 volt, or you can choose the 5 volts by setting these as 3, which would be 0, 0, 1, 1. No, I'm sorry. It's these bits up here. These bits up here. So 3 would be 1, 1. Or you could set that with a value of 1, 0, 1 in binary. I'll give you an example. I realize I confused you with what I just said. I'm going to give you an example of this, right? The very last register that we have to worry about with this thing is the ADC SRA. Wait a minute. There are. Let me back it up here. All right, we just looked at this AD MUX register. Now I want to look at the ADC SRA. Okay, ADC SRA. That stands for Analog to Digital Converter Status Register A. And so let me just sort of walk you through the things that matter here. ADEN. analog to digital enable, right? And that's this bin up here. You put a 1 up there to enable that thing. That means turn it on. If you don't do that, it's disabled. And what does it mean when it's disabled? It means this part of the chip is not powered up. It means it's not consuming power. And for the vast majority of applications where you have an 8-bit controller, they're operated by batteries, and you care about battery life. So every time you bring up a peripheral, you enable a peripheral, you're applying power to that part of the chip, to that functionality. And so by default, when you reset or power up one of these things, a lot of the peripherals are off. When you want to start to use the ADD converter, what you do is you put a 1 in that bit, and that will enable the device. So writing this bit to 1 will enable, and writing it to 0 will disable it. Okay, so when we're getting ready to use it, we'll just enable it. When you want to start a conversion, you just put a 1 in that bit position. You're going to put a 1 there. Okay. What else? When you tell it to start converting, it's going to do its successive approximation thing. It's going to take a certain amount of time for that to take place, and then it'll be done. And then what it'll do is it'll throw up a 1 in this bit position. It will throw up a 1 down here. So what we're going to do is we're going to just be waiting until we see a 1 in that position. That's analogous. You may recall when we talked about the UART, when we said, let's transmit something, like let's transmit the letter G out of the UART. Well, the UART, the universal asynchronous receiver transmitter, what we did is we gave the UART all the bits, all the ASCII bits for the letter G, and then the UART clocked them out 1 bit at a time at our baud rate, and then added a start bit and stop bits and sent that whole frame of data over. It takes time to do it. And so what we did is we waited until the UART was done doing that before we sent another character. So we had this, we called it polling. We were polling the status bit of the UART register until it was finished. Likewise, we're going to do that here. We're going to keep polling or looking at this bit until this thing becomes high. And at that time, we'll know that it's finished converting. Okay. The last thing we have to set down here is the pre-scaler select. That's going to determine the clock. And I'm just going to make this easy for you. On that one, it's called a 7-bit pre-scaler. All I want you to do is set those equal to 1. And what that'll do is it'll take our 16 megahertz clock and it'll divide it down to 125 kilohertz. Okay, I'm going to take all of this now and I'm going to kind of roll it all up in a cookbook formula here. What are the steps? And this is as described by the author of our textbook on his slides. So first, whatever pin you're going to use, make it an input pin. Choose the pin you're going to use, right? Whether it's 80, 81, 2, 3, 4, 5, make it an input pin. We're going to enable the analog to digital converter. We're going to set the conversion speed. We're going to select the reference voltage, and we're going to tell the analog to digital converter which input channel we want. Right? First, we have to make it an input channel, right? Then we're going to tell the analog to digital converter this is the input channel we want, and then we'll start the conversion. Right? We're going to write a 1 to a certain bit, and then we're going to wait for the thing to finish converting. And then after it's done, we're going to read the 10-bit value. We're going to read both the analog to digital converter lower byte and the analog to digital converter high byte. All right, and that'll get our output. If we want to read again from the same channel, you just go back up here and do it again. And if you want to change anything, you can go back up and and change reference and things like that. Okay. Yeah. So someone's saying there's so much. So Sebastian makes an interesting point. I never realized there's so much inside the Arduino function Arduino read. So what Arduino scripting language does is it hides all of this complexity for you. And that's fine for for hackathons or for some quick demos and things. But if you're really building something where you really want tight control over the resources, you want to really make good use of all the different pins on the device, you want to shut things down to power them down to save battery energy, you want to optimize speed, you want to communicate off the device, you want to do all this kind of stuff, that's when you want to get under the hood. You're not going to be using Arduino scripting, you're going to be doing it this way. You're going to hire an ECE person that knows this stuff. So yes, there's a lot underneath all of the Arduino script functions. Okay, so all those instructions are just now shown with this sort of picture here, and it's all, I've got all this stuff plastered on this slide. I'm just going to show you how we take those instructions and turn them into code. So make the selected pin an input pin. So let's assume here that I want to make PC0 as an input pin. So I'm just going to take a data direction register C, and I'm going to set PC0 low, right? And in this case, I'm leaving all of the others untouched. So this would just set that pin low and make it an input pin. Okay, step 2, I'm going to enable the analog to digital converter module. Right, to enable it, what that meant is I have to put a 1 in bit position ADEN, and this is the command that does that. I'm going to go to the analog to digital converter status register A, and I'm just going to put a 1 in bit position ADEN. Select the conversion speed. Okay, now on that one, what I did is I just went by very quickly. I just said set them all to 1. Which means in this bit position and this bit position and this one, we're setting those all to 1. The next thing is I'm just going to combine all this together. What I've got is a 1 in 4 different bit positions. So it would look like this. I put a 1 in this uppermost bit position and those 3 least significant bit positions. And that just corresponds to the hex number 0x87. So you could take all that and roll it up and just assign hex value 0x87. What that will do is it'll enable the analog to digital converter, and it'll set it to sample at a speed of 125 kilohertz with a 16 megahertz clock. Okay. Okay. The next thing we have to do is select the voltage reference and the input channels. Okay, that's over here. And so if you just give it the command ADMUX equals 0x40, that corresponds to this bit pattern. What that would correspond to is analog to digital converter C0, right? That corresponds to pin C0. That's just choosing that one from among all of them. That detail is sort of shown down here. Okay, and then also we'll choose VREF equal to 5 volts. Okay, the next thing, activate the start conversion bit by writing a 1 to the ADSC bit. Well, here it is. We put a 1 in the ADSC bit. Okay, we wait for the conversion to be completed by polling the ADIF bit and waiting for it to go high. So what we're doing here, this line here, you've seen this before with the UART. We're just staring at one bit in there, and we're waiting for it to go high. So we've got while that bit equals 0, wait. You see I have a semicolon there. That will just be a loop. This is called polling. We're just polling that bit. We're waiting for that bit to go high. And when it's high, the conversion is finished. Finally, when that's done, we're going to read the low byte and the high byte. And that's just shown here. Digital word, this is going to be a 16-bit word. It's going to be the low byte or the high byte shifted all the way to the left. So now I'm going to just take all of this and I'm going to put this in code. Right, here we are. Okay, I want to stop this video for a minute. So everything that I just sort of talked about is all encapsulated in this code. And you can just use this code for this lab experiment. This is the only lab experiment where we're going to be using the analog to digital converter. The other lab experiments that we've got, the 2 remaining, won't be using the analog to digital converter. So what we're going to have in here is I've sort of hard-coded everything I just described. These 2 lines here effectively initialize the analog to digital converter. We're going to select ADC0 as our input, and we're setting the reference at 5 volts. This one will enable it. This will set the speed at 125 kilohertz. So that enables it, gets it up and running, tells it what to use for VREF, and tells it where to get the input. And then in our while loop, here I'm telling it to start converting. I'm waiting for it to be done. And then I read the digital value. all this stuff you've seen before. What I'm going to do is take that digital value, and I'm just going to send that to the screen via UART. So all I'm doing in this loop is I'm just going, first I initialize the analog to digital converter with this code here. And then we go into a while loop. I sample it. I wait until I'm done sampling. I read that 10 bits of information. I store that in a word called digital value. I use the ITOA command, which converts it to a string, and then I just write that out to the serial monitor. And, you know, I'm using the function send string and UART send, which are these functions that we use often. I've got those functions copied down here. Okay, so now in the video that I'm going to show you, I'm not using the temperature sensor. What I've got here, notice I have the analog, I have my Arduino, and then in a red wire, I've created a 5-volt rail up here. Okay, black wire, I have the ground rail. I'll always use a red wire to connect directly to 5 volts, and I'll always use a black wire, you know, connected to ground, right? You know, if you know, people say, what would be the things that you were going to bring with you if you were going to be trapped on a, you know, desert island somewhere? I'd make sure I have a red wire and a black wire to connect to my VCC and ground. And whenever I give you a circuit to look at, it can be a complicated nest of wires. Look for the red wire, look for the black wire. Those are going to be your 5 volts and ground. Okay. The circuit that I've got is just a little ladder network. I've got 4 1K resistors connected in series. So this first resistor is connected up here to 5 volts. And then I have 2 resistors that are connected in series here, 2 resistors connected in series here, and the last resistor is connected down here to ground. So by having 4 identical resistors in a ladder network, I'll have 5 volts up here, right, 5. And then down here, I should have 2.5, 2.5. All right, and then, whoops, let's see. Yeah, 2.5 should be right here. All right, but I should have 1.25, 2.5, 3.75, and 5. So this was just a simple way for me to create an analog input signal that we could sample that has some sort of known voltages. They're going to be 0, 1.25 volts, 2.5, 3.75, and 5. Okay. Now, what are the corresponding digital values going to be? Well, we've got Vref equal 5 volts, right? So 0 volts, when I have this input, which is on this yellow wire, when that's down on that ground rail, we should be reading a digital count of 0. When I have that yellow wire all the way up top at 5 volts, we should be reading 1023. When I have that red wire on this node right here, right? No, on this one right here, right? I should be reading halfway between 0 and 1023. That's like 512. So I'm just going to show you the example here when I run this, and you're going to watch me picking up that red wire and moving it around, and you'll see on the scrolling display what the corresponding digital values are. Okay, so let's go ahead and here I'm picking it up. Okay, so it's 254, it's a quarter of the way. Okay, now it's halfway. 3/4 of the way. All the way up at the top, 1023. Okay, now I just take it out and notice I'm going to grab it with my fingers and notice it's bouncing around. It's a floating input. It's not connected to anything. You're getting garbage values. Be careful of floating inputs. Okay, now I'm back to ground. All right. One thing you may have noticed, it wasn't exactly 512 here. It wasn't exactly a quarter, half, and 3/4. And that's because these resistors that I've got are not all exactly 1 kilo. right? These resistors, they really only have a tolerance of about 5%. You know, they're not all nominally 1 kilo ohm, but they can all differ by a small amount. Okay, so I just wanted to show you a complete piece of code and then an example where we're just sampling an analog signal and then we're just writing it out to. Have I gone over? Looks like I've gone over time.
Yes.
Yeah, okay. Okay, I got so into it. Okay, I'll finish here. I just want you to know the very last slide here is I just sort of do the same thing, but I'm also, and you can take a look at it.